slides are up. Good. So let's get going. Last talk before the break. What I want to talk about today is the Open Virtual Platforms APIs and how they are enabling high-quality RISC-V models. I'll talk first about use cases and the requirements for the RISC-V models, talk about the model architecture, talk about the APIs, some case studies, and then sum up and get us to our break. So let's start first with the use cases and requirements. And here we've got a number of use cases up here, starting with compliance testing and software development, architecture exploration. I'll point out, actually down lower right here, the processor verification and virtual prototypes are also pretty key use cases for these. So the model requirements then are driven by those use cases, and it's a lot more than just an instruction set simulator. Of course, we have to model the ISA, including all versions of the ratified spec and stable unratified versions. You have to be able to easily update and configure the model for the next project. You cannot have a model that's built just one-off. It needs to be user extendable for the custom instructions, CSRs, et cetera. You need to be able to model actual IP in case you are coming from a point where you're licensing from Andes or Sci5 or ARC5 or MIPS or whoever. You need to have a well-defined test process for the model. So it's great to be able to build a model. There are a bunch of open source models in the community, but if you add something to that, if you want to take that, how are you going to test that? Is there a well-defined test procedure for that model? So you need to have that. Then you need to be able to interface to other simulators, to System Verilog, to System C, potentially other third-party tools, including debuggers, GDB, Lauterbach, GHS. There are various others around here, Ashling as well. Interface to software analysis tools, including being able to see the internal state of the processor, and architecture exploration tools. So the model has got to do a lot. If the model doesn't do that, if you don't have a single model for that, if you're using multiple models here, then you're going to have a disconnect someplace. So for example, if you're using different models for software development and hardware verification, different reference models, then potentially you're going to have a bug in something or just a mismatch, or your two teams interpreted the spec differently, and that's going to be a problem. So on to the model architecture. The Empiris FPM, fast processor model, RISC-V processor models. We've got a block diagram here. It looks just like your processor. We've got all the architectural elements in that processor. These models are built in C using those OVP APIs. The APIs are supported by a simulator engine, and all models have both a C and a System C TLM2 native interface. The models are quite flexible. There are ways to deal with shared resources, libraries that can be brought in. So quite a bit can be done with these. We're trying to actually meet all those requirements that I stated. So what does this actually look like as a model? So we're going to start with a base model where the base model implements the RISC-V specification in full. It's fully user configurable, not only on each extension, but on each version of each extension, because there have been multiple versions of these extensions. They were stabilized early. People started designing to those, and the model needs to support those versions. It's got predefined configurations, custom instructions for the processor IP vendors. User extensions then are built in a separate library, in a separate side file. And we're doing that so that the base model is not perturbed. that means that that base model gets used by all the RISC-V models that are built using this, this architecture. So what that means in sort of the real world is that over 150 different companies, organizations, universities have used that base model, and it's pretty rock solid at this point. So all that comes together and becomes the Empiris FPM, the base model, the configuration, the custom instructions. And by building it in this way, any tools that are associated with that model are going to be usable with the custom instructions. So one of the use cases that we had that I'll talk about here is adding custom instructions or architecture exploration. In the RISC-V world, as we know, what we're trying to do typically is to add custom instructions to improve the performance of a specific applications or a set of applications. And so that's a great thing. What we're creating are domain-specific processors. We've seen a number of examples of that just in the last few presentations. The models let you explore the custom instructions quickly. It's a lot easier, actually, to add custom instructions into the model than into RTL. It's a lot easier to run your application on that. You've got analytical tools available, and so we can create this nice iterative loop here and go from analyzing the application and creating a baseline, adding the custom instructions, analyzing those custom instructions, and then iterating. And that can be done actually quite quickly. So on to the APIs. With the, let's just build this out here. So we've got the base model, the configuration, the custom instructions, and these are supported and built with the OVP APIs, and supporting that is a just-in-time binary translation simulation engine. So those APIs actually have two sets, essentially. One is model functionality, so just what the processor is doing. The second is processor analysis tools. So there's a separate set of APIs that enables the tools that we're building here. Again, this is a just-in-time binary translation engine, so what we're doing is translating RISC-V instructions to x86 instructions on the host PC. And then for those analytical tools, for this analytical instrumentation, instead of instrumenting the source code or instrumenting the model, this is actually done in the simulator. And so it's completely non-intrusive, which is really important from an analytical perspective. These APIs are publicly available. There's a GitHub repo there for the APIs. The APIs have actually, they were first released in 2008, and these APIs have been used to build models of 18 different instruction set architectures, including ARM, MIPS, Renesas, down the list, but also including 3 proprietary APIs where users just took the APIs and started from scratch, building their own processor models. So this is actually well documented and user friendly. So why does this architecture work so well? First thing is performance optimization. When a specific API's performance is improved, it impacts all the models using that API. So the APIs are effectively in that simulator. They're not in the model, the execution of those APIs. So anything that's done to the API is going to impact all the models. That also flows to maintenance. So maintaining the models is a lot easier because if there's a bug, if there's a problem with the functionality of a specific API, or if something is being extended, if you do that for the API, it's going to happen for all the models. Third thing is documentation. So having a clean set of APIs, a well-documented set of APIs, makes it easier to document the model structure. And actually, what we've done there is automatically generate documentation for the RISC-V models. So that's a push-button thing now that gives you what features are in there, but also gives you limitations and what's not in there. And then tool interfaces. I mentioned this before, but if you're building to the same set of APIs, and your tools are based on those APIs, then any new model is just going to work, and that's a really good thing as well. As a result, fewer engineers are needed to develop and maintain these models, and as a result, users can easily add custom features to their models and have those models be used by their teams quite easily. So, case studies. Let's take a look at this. So now we've got the Empirus FPM model here in all these use cases. And I'll go and focus on the processor verification and virtual prototypes. And again, I'll make the point that using the same model for both hardware and software verification enables ease of use, enables reduction in this case, in bring-up time. So specifically, maybe an extreme case, but we had one user that built a virtual prototype. Well, their platform was, I think, 4 different RISC-V processor cores, doing everything from microcontrollers to application processor to AI accelerator, over 150 different cores on that. They're able to simulate, they're able to do DV, and when first silicon came back, this came up in the lab in a matter of days, not weeks or months, but days. So on the verification side, that model now can be used as a reference model. So reference model in a DV flow. We've been doing this for a few years now. We've collaborated on a DV flow with OpenHW Group and with various members of OpenHW Group and other customers. This is a asynchronous continuous compare methodology, which handles pretty much everything you're trying to do in the RISC-V community. Virtual prototypes enable early software development, and we've got all the models here. A key thing here on the virtual prototypes, again, is performance, because software developers want very high performance in their simulation. And so these virtual prototypes with the Empirus FPM models are running in the range of 500 to 1,000 million instructions per second. Performance on a simulator, booting Linux in about 6 seconds. Peak performance is a lot higher on contrived benchmarks, but this is normal workload performance. As a case study here, we'll look at Cha-Cha-20 encryption instructions. I'm running a little short, so I won't go into all the detail here, but without the custom instructions, it's about 1.3 billion instructions to execute. Profiling showed that this specific process line function took 21% of the execution time. We're going to use the APIs to add the instructions into the model, and then actually having defined the decode, we can define the actual behavior of those functions. And then what happens is that with that architecture, with that model built on APIs, with the simulator underneath, the simulation performance increased actually from 1.1 to 1.3 billion instructions per second. The process line function went from 21% of execution time to 15%, under 15%. And these tools, instruction tracing, actually we see the Cha-Cha-20 instructions in the debugger disassembly. So these tools just worked. We didn't have to do anything extra there. So just summing up here, the RISC-V processor models are at the heart of RISC-V processor development, all those different use cases. The API-based model architecture more easily meets the needs, meets all these use case requirements. Also, the API-based architecture provides additional benefits, quality, flexibility, extensibility, high performance, ease of documentation. So we've got these in the Empiric's FPM models. And I would say about these models, just one real plug here is that it's silicon proven at this point. There are over 30 tape-outs of SoCs that have been enabled by RISC-V processors verified with the Empiric's FPM golden reference models. Thank you very much.
So we are really at the hour, but we do have like time for one little question for Larry. Otherwise, you may join him or find him in the booth, I think so.
Yep. You can find me at the Synopsys booth, or there's my email address, now Synopsys. So please, looking forward to talking with you. Thanks.
Thanks again.